Now let us find gravitational field to spherical shell of mass capital M and radius r. Suppose you are given a spherical shell and you want to find the gravitational field inside and outside the spherical shell. Suppose we have spherical shell over here and we want to find gravitational field inside and outside. This is spherical shell of mass M. So shell means hollow sphere. And we want to find gravitational field inside and outside. Suppose this is center and this is radius r. Make it capital R. Alright. So we want to find gravitational field as a function of r. Let us find gravitational field as a function of small r. So we have to find gravitational field as a function of r means what? You have to find gravitational field inside and you have to find gravitational field outside. So suppose take case 1. Suppose we want to find gravitational field inside. Suppose you have a point P over here and you want to find, say, point P is lying at a distance of smaller, and we want to find field at this point P. So here small r is less than capital R. We want to find gravitational field inside. That is, we want to find gravitational field inside. So we can make use of Gauss law of gravitation. So for getting a gravitational field at point P, first of all we have to choose a Gaussian surface. So I told you in the last video that the Gaussian surface should be spherical to the mass distribution. Sorry, not spherical, symmetrical. Gaussian surface should be symmetrical to mass distribution and it must pass to the point where you want to find field. So mass is spherically distributed on the surface. So we will take the Gaussian we will choose is, we will take a sphere of radius small r. So we have two consideration. One, Gaussian surface should be Gaussian surface should be symmetric to mass distribution and it must pass to the point where gravitational field is to be found, right? So the first consideration told you the shape of Gaussian surface, that it should be symmetrical to the mass distribution, and second point gives you the size of Gaussian surface, that is Gaussian surface must pass to the point P, so that gives you the size of Gaussian surface. Okay, now this is outward drawn normal, this is Gaussian surface, this is the volume enclosed by it. So any normal which is lying outward from the volume, that's outward drawn normal. So we'll find the flux first, G dot NDS, and G, if it is there, would be attractive. Gravitational field is always attractive, so it will be radially inward. If it is there, it will be radially inward. We don't know whether it is zero or non-zero, but if it is non-zero, it will be radially inward, whereas n is outward drawn normal. So G dot n is going to be minus G, and G is always a function of R. G is a function of R only, and the Gaussian surface that we have taken is spherical Gaussian surface. So R will have a same value at each and every point. So if G is there, it will be a function of R only, and since R is having constant value at each and every point, so G will have a constant value at each and every point on the Gaussian surface. So I can take G out, that is G into 4 pi r square. And what is the mass enclosed? Mass enclosed is 0 because it's hollow. Mass enclosed means mass enclosed by the Gaussian surface. So from the Gauss law of gravitation, we have G dot NDS equals to 4 pi gm, where m is the mass enclosed by the Gaussian surface. So this is G into 4 pi r square. So that means G is 0 inside. G is 0 inside. Okay, G will be 0 inside. Now, so that is for R less than R. Now let's find the gravitational field for R greater than capital R, for outside. Let's find out gravitational field outside the sphere. Case 2. R is greater than R. Suppose point P is outside now. Point P is outside. So let's take a Gaussian surface. You can take this Gaussian surface, symmetrical to the mass distribution and passing to the point P where gravitational field is to be found. So this is your Gaussian surface and this is your radius R, right? On this Gaussian surface also, N lies in radially outward direction. So G dot NDS is G, if it is there, it will be radially inward, because G is always attractive. If you put any mass over here, it will be pulled in inward direction. So gravitational field, how I have defined gravitational field due to any object at any point P is the force experienced by 1 kg of mass placed at that point P. So if you want gravitational field at point P, you just put 1 kg over here and see in which direction it's getting pulled. So it is pulled in radially inward direction. So gravitational field will always radially inward direction, and any radially outward. You understand logic? It's attractive. It's always attractive. So if this is a sphere, want to get the sign of direction of gravitational field, you just put 1 kg mass over here. So it will be attracted towards the shell. So it will be always in inward direction, and N is outward or normal. Gauss law makes it very clear. N is outward or normal. G is radially inward, N is outward, radially outward. N is radially outward. Of course, because the Gaussian surface you have taken is cell. So normal to the cell is radially outward. Normal to the sphere is in direction of radius. Right. So G dot N will be G into cos 180, which is minus G. And G will be function of R only. G will be function of R only, and R has got a constant value at each and every point. So I can take G outside. This becomes G into 4 pi R square. Right. And what is mass enclosed? Mass enclosed is the whole mass is getting enclosed inside Gaussian surface. Mass enclosed is capital M. And now we can use Gauss law of gravitation. We have found the flux. So this will give you minus G into 4 pi R square. So your G is minus G by R square. Or if you want to write in vector form, this will be this. So this is G. Inside is 0. If you take a hollow sphere, inside gravitational field will be 0, and outside is minus Gm by R square. So this is how you can find gravitational field. This is how you can find gravitational field to a spherical shell. Spherical shell. Okay. We have found gravitational field due to ring, we have found due to disk, due to solid sphere and spherical shell. In finding gravitational field due to solid sphere and a spherical shell, we have used Gauss law of gravitation. Gauss law of gravitation. This can be found without using Gauss law of gravitation also, but that will take a lot of time. That will take a lot of time. So using Gauss law, especially for those mass distribution which is symmetrical, will be very useful for you. Right, and you will have extensive use of this Gauss law of electrostatics in your next topic, that is electricity magnetism. This is a variant of just Gauss law of electrostatics. So we'll make use of such a thing quite often in electricity magnetism. Okay, so this is how we can find out the gravitational field to a spherical shell.